We now introduce one of the most popular machine learning model called Gaussian mixture model. The idea of Gaussian mixture model is that theoretically, by using a sufficient numbers of Gaussian and by adjusting their means and covariance as well as the coefficient in linear combination, almost any continuous density can be approximated to arbitrary accuracy. So in a world, for any distribution, we can use appropriate numbers of Gaussian mixture with appropriate uh, coefficient to combine them and approximate any distribution. So here we can see some example. Assume that we have the data point in green distribute like this. And if we use one Gaussian mixture, two-dimensional Gaussian mixture, we can estimate the distribution like this. So we can imagine that the peak of the Gaussian is around here, and this mountain, we can see this Gaussian distribution distribute from the left bottom to the right top. Okay, and obviously this is not a good approximation. But if we use two Gaussian mixture, then we can model the two cluster of these data points. So if we use two Gaussians, we can more appropriately describe this set of data point and this set of data point. So we can describe the total distribution based on the combination of these two Gaussian mixture. So these two are two-dimensional case. For one-dimensional case, for example, given the distribution represented in the red curve, then we can use three Gaussian mixture, this three Gaussian mixture in blue, to approximate the red distribution. So we can use three blue Gaussian mixture with appropriate mean and the covariance as well as the linear coefficient to combine or to linearly combine these three Gaussian mixture to approximate the red distribution. Okay, and this idea can be extended to high dimensional space, and that's the basic concept of Gaussian mixture model. So mathematically, we can describe any probability distribution, for example, probability distribution of x by a linear combination of k Gaussian mixture. So here we linearly combine k Gaussian mixture. Pi k is the linear weight for the k's Gaussian mixture, and the nx given mu k sigma k is the k's Gaussian mixture. And we can specify mu k and sigma k to specify the k's Gaussian mixture. Okay, so each Gaussian density is called a component of the mixture and it has its own mu, mean, and sigma. So here is another two-dimensional Gaussian mixture example. We can linearly combine these three Gaussian mixture to form a very complex distribution. And if we draw it in a three-dimensional space, we can see this is a very complex distribution in three-dimensional space. So for any complex distribution, we can use appropriate numbers of Gaussian mixture to combine them. And from the sum and the product rules mentioned in probability class, the marginal density is given by this formula. So Px is equal to summation Pk multiply Ps given k. So you can compare these two equations. Then we will say that we can view pi k as Pk. So pi k is the linear coefficient of the case Gaussian mixture, and we can view it as the prior probability of picking the case component. And the density of the probability X condition on K. So we can see that probability X given K can be described by Gaussian mixture, by a Gaussian mixture. Okay, so as we say before, this is actually the likelihood. Okay, so the likelihood function can be described by a Gaussian mixture. And from Bayes' theory, the posterior probability pk given x is given by the following formula. So pk given x is equal to the total probability and the probability pk multiply ps given k divided by the total probability. And right now, pk multiply pk times ps given k is modeled by pi k times a Gaussian, the case Gaussian mixture, and the denominator is the total probability. So the Gaussian mixture distribution is governed by the parameter pi, mu, and sigma. Okay, so how do we describe a Gaussian mixture model? We have to describe the linear coefficient, uh, the means of the Gaussian mixtures, and the variance of the Gaussian mixtures. So one way to set these parameters is to use maxima likelihood. So how do we determine these parameters? We use the maxima likelihood method. So we take the log likelihood. So here is the model, and this is the data point. So PS given model is actually the likelihood, and we want to maximize the log likelihood. And as we can see here, the likelihood here is the we can see is p x given k actually, and by taking the log, we can see the form. Okay, so we can assume that different mixture are independent and identically distributed, so that we can, if we take log, we can we can sum the log value of each Gaussian mixture. Okay, because we assume that different mixtures are independent and identically distributed. So in the case of a single variable, the Gaussian distribution is in the form. Okay, so now in this slide, we introduce the formulation of Gaussian distribution. So if there is only one variable, or if the data is only one dimensional, then the one-dimensional Gaussian distribution is look like this. So we can expect that we can characterize this Gaussian distribution by the mean and the variance. And you can see this mathematical definition when the data point x, the data value x, is far from the mean, then the value here will be large, and the value by take the minus and take exponential, the total value will be small. So that's why we see a Gaussian mixture is look like this. Okay, so here is mu, and if the x is far from mu, then the probability here will be smaller. Okay, so this is one-dimensional Gaussian distribution. For d-dimensional vector x, so we have to construct a d-dimensional Gaussian distribution that would be like this. So we also specify this Gaussian distribution by mu and sigma. But here, mu is a vector. Sigma is actually a matrix, the covariance matrix. So this is the formulation of d-dimensional Gaussian distribution. We also calculate the difference between data point and the mu, but right now we have the vector form, and this is the covariance matrix not only a single covariance value. And in two-dimensional space, two-dimensional Gaussian is look like a circle, okay, and the probability at the center is the highest. And in a three-dimensional space, the Gaussian distribution it look like a sphere, and the center has the highest probability. The most important problem now is how do we learn the parameter of pi, mu, and sigma. So based on the log probability, we can divide it the log probability of different Gaussian mixture, and we try to find the best parameters to maximize the log likelihood. How do we do that? Based on some optimization theory, we can set the derivative of the log likelihood with respect to the means mu of the Gaussian component and set the derivative to 0. So this is a very popular way to find the optimal setting of a objective function. And right now, we want to find the way to set up mu. So we calculate the partial derivative with respect to mu and set the derivative to 0. And after several mathematical derivation, this is the partial derivative of with respect to mu, and we set it to 0. And this term we define it as a gamma z n k. We can see that after some mathematical derivation, the mu k is actually the average gamma z n k multiplied by the data point xn. So the physical meaning here is that how can we get the mean of the case Gaussian mixture? The answer is we just linearly combine the data point by the posterior probability of the case Gaussian mixture, okay, and take the average. So this is the what we do to update the mean of the case Gaussian mixture, where nk is the summation of all gamma z and k. So the mean mu k for the case Gaussian component is obtained by taking the weighted mean of all the points in the dataset, in which weighting factor is given by the posterior probability gamma z and k. And to find the best covariance, we also set the derivative of the log likelihood with respect to sigma k, and set the derivative to 0. And also, after many mathematical derivation, we can get the sigma k is equal to this value. And we can see that this part is actually the covariance, and this part is the posterior probability. So again, each data point weighted by corresponding posterior probability, each data point's covariance weighted by corresponding posterior probability, and the sum together, and then take the average, we get the covariance value. For estimating the mixing coefficient pi k, we also maximize the log likelihood with respect to the missing coefficient. The constraint is we want the sum of missing coefficient to 1. So this time we use Lagrange multiplier and maximize the following quantity. So this is Lagrange multiplier, and this is the constraint that the pi k summation of pi k is equal to 1. And then we can write down this Lagrange function, and then again take the derivative of this Lagrange function and set it to 0. And finally, we can imply, we can get the following conclusion. If we multiply both sides by pi k and then sum over k, making use the constraint, we find lambda is equal to minus n. And using this to eliminate lambda and rearranging, we can obtain pi k is equal to nk divided by n. So what does this mean? The missing coefficient of the k's component is given by the average responsibility which that component takes for explaining the data point. Okay, so here nk and n is the total numbers of Gaussian mixture, and nk is the posterior probability of the k's Gaussian mixture. So pi k means the power or the responsibility of the k's Gaussian mixture to explain the data points. Okay, so this is what we do. Of course, we skip many mathematical details, but this is what we do to estimate pi k, mu k, and sigma k. And if you understand this very well, you may find that it seems that this is a chicken and egg problem, because to estimate pi k, we need to calculate this value. Okay, and then we need the mu k, sigma k value. Okay, and to estimate, if we go back to previous slide, how can we estimate sigma k? We actually need to use the gamma z and k. And what is gamma z and k? Gamma z, to calculate the gamma z and k, we need pi k, mu k, and sigma k. Okay, so in a world, to estimate mu k, we need mu k, sigma k, and pi k. So this is a chicken egg problem. Okay, initially we don't know mu k, sigma k, and pi k, right? So, but we still need to estimate the mu k. Okay, so how can we solve this problem? We can use the expectation-maximization algorithm, or called EM algorithm in short. So we first choose some initial value for the means, covariance, and the mixed coefficient. So we just randomly initialize the values for mean, covariance, and the mixing coefficient. And then we use the current parameter to evaluate the posterior probability so that we can get the gamma, z, and k value. And based on gamma, z, and k, we can re-estimate the mean, covariance, and the missing coefficient, just as we mentioned in previous slides. So right now, after maximization, we have newer means, covariance, and the missing coefficient, and then we can evaluate the posterior probability again, and then update them again. So we can do the expectation and the maximization in an iterative way. So each update to the parameters result from an E step followed by an M step. That is guaranteed to increase the log likelihood function. And the EM algorithm is actually commonly used in optimization when you face a chicken egg problem. So here are some examples showing how the learning process can learn better parameters to fit the data point. So given the data points, so initially we just randomly put the Gaussian mean and the variance, as well as the coefficient, the combination coefficient. And so initially this blue Gaussian can describe the data point, and this red Gaussian can describe the data point for some extent. And after one iteration, after one update, we can largely change the Gaussian mean to here and here, and change the covariance, so that you can see that these two newer Gaussian mixture can more appropriately describe the data point. But that is not enough. So after 5 iteration, after 2 iteration and 5 iteration, or after 20 iterations, these two Gaussian mixture can well approximate the distribution of the given data points. And that's the process of the whole EM algorithm. And this is the mathematical definition about the EM algorithm. So initially, we randomly set the mu k, sigma k, and the missing coefficient pi k, and then we evaluate the posterior probability gamma znk, and then based on gamma znk, we can update the new mu covariance and the missing coefficient, and then we can repeat this again and again. And of course, based on the new mu, sigma, and pi, we can estimate newer log likelihood. We can check whether it is converged or not. If not, we just go back to step 2 and do EM iteratively. Let me show you a case study applying Gaussian mixture model in multimedia content analysis. In this paper, published in ACM Multimedia year 2004, the paper title is a new method to segment play field and its application in match analysis in sports video. In this paper, they model the play field based on Gaussian mixture model. For example, the basketball field, the soccer field, okay, the soccer field. And for taking the soccer field, for example, we can imagine that the soccer field are mostly green, right? But we do have very many variation on green. We have light green, we have dark green, we may have shadow on green. So actually, it is not appropriate if we just define the soccer field as green. Okay, it's even not accurate if we just set up a color range like corresponding to the soccer field. So it's difficult for us to set up a soccer to set up a field, a range to describe the soccer field. Okay, it's really difficult, especially when there is different weather condition, or when there are different broadcasting TV channels. So it's difficult to automatically describe the soccer field. So in this work, they extract the video frame and then they sample the pixels inside the soccer field. And then they use the Gaussian mixture model to describe the green color inside the soccer field. Okay, so they assume that the variation of the green pixels in soccer field may be something like this. That's quite complex. Then they use many Gaussian mixture to describe the distribution of the soccer field. Okay, so that they can more appropriately estimate, given the pixel, they can estimate the probability of this pixel belonging to soccer field. Okay, so that they can detect the pixel in soccer field, and after some post-processing, they can get good result. So the condition density of pixel psi belongs to the playfield phi is modeled by M Gaussian density. So the mathematical definition is that this. So given the playfield region, we want to estimate a pixel belonging to soccer field, the probability of this pixel belonging to soccer field. And this probability is described by, this is weighted combination of Gaussian mixture. Right here, they describe the Gaussian mixture by BI function. So here are some detection results, and we can see that they can get much more accurate result. So for different soccer field, they can detect it very correctly. And also, not only for soccer, they can also detect like badminton or tennis or basketball. Okay, so this is one case study of applying Gaussian mixture model in multimedia content analysis. And if you are interested in developing your own Gaussian mixture model, you can refer to this resource, like the NetLab, okay, which is a very famous library for you to develop the Gaussian mixture model. Or you can use some MATLAB toolbox to do so.